Hello, my name is Alexander Takla, and I'm a PhD student in particle physics, which means I study the particles that make up our universe. My research focuses on one of the most interesting and mysterious concepts in all of modern physics, dark matter. Dark matter is a different type of matter that cannot be seen directly. Unlike ordinary matter, the stuff we deal with in our day-to-day lives, dark matter does not interact with light at all, so it's completely invisible to both microscopes and telescopes. However, we know it must exist because of its gravitational effects. When astronomers study how galaxies rotate, they find that visible matter alone cannot explain what they observe. There must be some additional unseen mass providing extra gravitational pull. That is dark matter, and it makes up 85% of our universe. We seek to understand its properties, including its mass and interactions with ordinary matter. One well studied model is WIMP dark matter, which stands for weakly interacting massive particles. In simple terms, there's a new type of particle that interacts very weakly with ordinary matter through processes including annihilation, shown here, and through direct detection or scattering, shown here in the middle. These extremely weak interactions make it very difficult to probe the experimental properties of the dark matter. Let me take a moment to orient you to the slide. Here, dm is the dark matter, OM is ordinary matter, and SI is the strength of interaction. Physicists have spent decades searching for WIMPs through direct detection. Here, a detector is built, like the one in the middle. It looks for collisions for dark matter particles among each other, similar to how two billiard balls collide on a pool table. So far, these experiments have not found evidence of WIMPs, and the field has reached a crossroad. There is a tension that exists between direct detection and annihilation. If the strength of interaction is large enough to produce the correct amount of dark matter, we would have already seen it in direct detection experiments. But if the strength of interaction is small enough to evade these searches, there would be too much dark matter left over today. This is where my research group explores new ideas. Instead of assuming a single type of dark matter, we study models with multiple dark particles. Note to the right, we have a DM2 and an SI2. These additional particles introduce a new process called co-annihilation. This is shown here on the right, where two different dark particles, DM1 and DM2, annihilate together. This allows us to avoid direct detection by setting the strength of dark matter interactions to be very small, but still have the observed dark matter from co-annihilation processes. Our group studies these multi-particle models in details and has identified new regions where dark matter could still exist. While the research is conducted at the University of Michigan, it extends far beyond the state, contributing to an international effort to understand the composition of our universe. Our work keeps Michigan at the forefront of discovery while leading to the global strategy for future dark matter searches, helping to answer one of the most fundamental and important questions in physics. What is our universe truly made out of? Thank you.